Okay, let's do one more example. In this example, we have water contained in the piston cylinder assembly, and it will undergo two processes in series. Initial pressure is 10 bar, initial temperature is 400 Celsius. In process 122, water is cooled as it is compressed at a constant pressure. This is a constant pressure process, and the pressure is equal to 10 bar. And then it's going to cool down to saturated water vapor state. So cool down to point G. That's process 122. And then process 223, water will continue to be cooled, but this time at constant volume. And then the final temperature is given as 150 Celsius. We're looking for three things. First one, the two diagrams. Second one, work per unit mass in kilojoule per kilogram. And part three is look for heat transfer per unit mass in kilojoule per kilogram. Okay, so we have two processes together. The first one is constant pressure cooling. The second one is constant volume cooling. Okay, so first we're gonna sketch the two diagrams. Just like before, we'll do the preparation and draw the vapor dome on each one of them. P versus nu, T versus nu. Draw the vapor dome. Steep, less steep, steep, less steep. Okay, so that's the vapor dome. Let's start from the first one, P versus nu diagram. P versus nu diagram. Okay, just like before, on a P versus nu diagram, we have constant temperature lines. Curve down, and then straight, and then curve down, curve down. Okay, let's call this one T1 line, meaning this line represents temperature T1. Every point on this line has the same temperature, and that is T1. Okay, so now we're gonna locate point number one. Locate point number one. So we know point number one is gonna be on this T1 line, but where is it? Where do we put point one? That means we need to find out the phase of point number one. For example, if point number one is superheated, that means we just put point number one on T1 line and then to the right side of the vapor dome. If point one is a mixture, then we just put point one on T1 line but within the dome. Okay, so in order for us to locate point one, we have to find out the phase of number one. How do we find the phase of number one? We can do this. Because we know the initial pressure is given, pressure P1 is given, and it's given as 10 bar. The initial pressure is 10 bar, so P1 is equal to 10 bar. Remember, if you want to start from pressure, you go to table A3. If you want to start from temperature, you go to table A2. So we go to table A3 and we start from we start from pressure P1, which is 10 bar. Table A3. Okay, let's go to table A3. And we start from pressure, which is 10 bar. 10 bar right here. This is 10 bar. And then from this 10 bar, what can we find? We can find a corresponding saturation temperature, 179.9 Celsius. This is the temperature when water starts to boil at this 10 bar. Okay, this is the boiling temperature at 10 bar, saturation temperature. Okay, so we write down this number. We found saturation temperature. We call it T-sat1, saturation at number 1. T-sat1 from the table is 179.9 Celsius. This is the temperature when water will start to boil, meaning G point, right? Okay, so what is the actual temperature at point number 1? Is it given? The initial temperature is given as 400 Celsius. 400 Celsius. So T1, the actual temperature is 400 Celsius. Your actual temperature is even higher than the boiling temperature. What does that tell you? Point number one must be superheated. Only superheated water vapor can have temperatures higher than the boiling temperature. So from here, we can say point 1 must be superheated. Okay, so now we can locate point 1 on P versus nu diagram. It has to be on T1 line, and then it has to be on the right side of the vapor dome. So now we put point 1 somewhere here. This is our point 1 on T1 line, and then to the right side of the vapor dome. Okay, so that's point 1. Next one, we need to locate point number 2. How do we locate point number 2? We take a look at process 122. Process 122. This is a constant pressure process, and point number 2 has to be saturated water vapor. So that means G point. So 122 is a constant pressure process, and number 2 has to be G point. Okay, so how do you sketch this on P versus nu diagram? 122, like we said, is a constant pressure process. And on a P versus nu diagram, pressure is the y coordinate, which means for 122, the y coordinate is constant. If the y coordinate is constant, then 122 must be an horizontal line. Okay, horizontal line. So you can sketch an horizontal line across point number 1. And then we say 122 must be on this dashed line. Okay, and where's number 2? Number 2 must be G point. Where's G point? G point must be on the dome. So this is number 2. And then we can connect 1 and 2 together. It must be a straight line. 1 to 2 must be a straight line. And this is my number 2, point number 2. Okay, 122, go straight to the left. It's a horizontal line. All right, so that's 122. And then 223. 223. Let's take a look. What is 223? 223 is a constant volume process and it's cooling. It's cooling down. Okay, 223, constant volume. So what's gonna happen to my x coordinate nu? Nu is equal to volume over mass. If volume is constant and we know mass is constant because it's a closed system, so that means nu is constant. So I have a constant x coordinate for process 223. For process 223, if the x coordinate doesn't change, it must be a vertical line. So 223 must be on this vertical line. We can sketch a vertical line across point 2. Okay, and then where's number 3? Point number 3 must be on this vertical line. So do I put point number 3 above number 2 or below number 2? Remember, 223 is a cooling process. If you cool it down, what's going to happen to the y coordinate, which is pressure? If cooling happens, pressure will become lower, which means the y coordinate will become smaller. If the y coordinate becomes smaller, you must go down. So 223 goes straight down along this dashed line. And point 3 will be somewhere here. Okay, and then you can make it look prettier by adding one more constant temperature line. For number 3, this is the constant temperature line representing T3. Okay, you can do the same thing for point 2, but it's not necessary. Okay, so this is the first diagram, P versus nu diagram. Okay, next one, let's do the second diagram, T versus nu diagram. On a T versus nu diagram, we have constant pressure lines. So let's sketch a constant pressure line first. You curve up, okay, so it's not straight. Curve up, and then straight, and then curve up. This is a constant pressure line. For example, we can call it P1 line, P1 line, or P2 line. Why? Because 122 is a constant pressure process. So P1 is equal to P2. So this line can represent both P1 and P2. Okay, next one, let's locate point number 1. Point number 1 has a pressure of P1, so it must be on P1 line. And then where on this P1 line? To answer this question, you just need to find out the phase of number 1. If number 1 is superheated, you just put it to the right side of the vapor dome. If point 1 is a mixture, you put it within the dome. And we said before, point 1 is superheated, so point 1 must be on P1 line and to the right side of the vapor dome. So we put number 1 here. Put number 1 here. And then let's locate number 2. 1 to 2 is constant pressure process. So 1 to 2 must be along this constant pressure line. And then do I go to the left or to the right? This is easy because we know point 2 is saturated water vapor, meaning point 2 is G point. And where's G point? There's only one G point here, right on the dome. This is where G point is, and also along this constant pressure line. So this is my point 2, 1, 2, 2. Okay, so that's 1, 2, 2. And then 2, 2, 3. 2, 2, 3 again is a constant volume process. So what's going to happen to the x coordinate, which is nu? Nu is equal to, again, same as before, volume over mass. Volume doesn't change for 2, 2, 3. Mass doesn't change because it is a closed system. So nu doesn't change. So for 2, 2, 3, the x coordinate nu is constant. If the x coordinate is constant, it must be a vertical line. So you can sketch a vertical line across point 2. And then 2, 2, 3. Where do I put number 3? I know number 3 must be on this dashed line. Do I put number 3 on top of number 2 or below number 2? Remember, 2, 2, 3 is a cooling process. So what's going to happen to temperature? Temperature will go down. That means the y coordinate will become smaller. If the y coordinate becomes smaller, you have to go down. So 2, 2, 3, go straight down along this dashed line. This is number 3. And then to make things look prettier, you can add one more constant pressure line for number 3. Curve up straight and then curve up. This line represents P3, the pressure of number 3. So this is the T versus nu diagram. Okay, so now we're done with part 1, sketching the 2 diagrams. Okay, and then we move on to part 2. Part 2 is to look for work per unit mass, and we want the unit of kilojoule per kilogram. How do we look for work? We can always try to start with the most fundamental equation for work. Work is always integral P dV, and the lower limit will be V1, but this time the upper limit will be careful here, it's V3, not V2, because the final point is number 3, not number 2. Okay, and then we can separate V1 to V3 into 2 steps. The first step is V1 to V2, 1 to 2, plus the second step, that is V2 to V3, PdV. Okay, we separate 1 to 3 into 2 steps, 1 to 2 first, and then 2 to 3. Okay, remember what kind of process is 2 to 3? Constant volume process. Constant volume process for 2 to 3. So what is dV? D means change. So dV is the change of volume. The change of volume in process 2 to 3 is 0. So the whole second term in the right hand side goes to 0 because volume is equal to constant. Differential a constant must be 0. So this term goes to 0. And then we only have one term left in the right hand side, which is integral PdV 1 to 2. And then let's take a look again. What kind of process is 1 to 2? 1 to 2 is a constant pressure process. Pressure doesn't change. Pressure is my integrand and pressure is constant. So you can take pressure out of the integrand. And then what is left is just V2 minus V1. And for this pressure, you can call it either P1 or P2. Doesn't matter because P1 is equal to P2 since it is a constant pressure process. Okay, and then let's recall one more time. Nu, the definition of nu is volume over mass. So we can rewrite volume. We can rewrite volume. We can rewrite V2 into mass times nu2 minus mass times nu1. And then we can take mass out of it. So it becomes P1 times mass times nu2 minus nu1. And then what we do is to move mass to the left-hand side. So the equation becomes work over mass, and that is equal to P1 times nu2 minus nu1. And we're looking for work per unit mass. So now we can clearly see if we want to find out work per unit mass, we just need to find three things in the right-hand side. They are P1, nu1, and nu2. What is P1? We already have it. P1 is the initial pressure. What is the initial pressure? It's given 10 bar, so we already have P1. And then what is nu1 and nu2? We don't know those two. We just need to find nu1 and nu2, then we're done. Okay, let's start from nu1. Let's start from nu1. How do we look for nu1? Nu, specific volume, is a property. If you're looking for the property, you always have to find out the phase first, and then you make a plan. All right, so what's the phase of point number 1? If you don't remember, you can go to the diagrams. Where's number 1? Number 1 is located to the right side of the vapor dome. So number 1 is superheated. If you want to look for any property regarding superheated water vapor, you always have to go to table A4. So now we know we must go to table A4 because point 1 is superheated. Right? Remember how to use table A4. We have to provide two inputs. The first input always has to be pressure. Okay, so we have to find P1. And then in addition to P1, we need one more. We said we already know P1. P1 is the initial pressure, is given as 10 bar. And then we just need one more term regarding point 1. One more property regarding point number 1. What else do we know about the initial state? We know the initial temperature, 400 Celsius. So we know T1. We know T1. So T1 is 400 Celsius. And from here, we can easily find nu1. Okay, so now let's go to the table A4. Let's go to table A4. Okay, so this is table A4. And remember, our pressure is 10 bar, so we look for the block corresponding to 10 bar. 10 bar. Where's 10 bar? Okay, there it is, 10 bar. This is the block we should be looking at. And then the second input we have is temperature. Temperature is the first column, and the unit that table uses is Celsius. Our temperature is 400 Celsius, so we find 400 Celsius right here. And then what is the corresponding nu? Nu is the second column, and don't forget a unit. So the corresponding nu will just be here, 0.3066 cubic meter per kilogram. So this is how you find nu1. Okay, so we go back to our notes and we write down the nu1, 0.3066. Don't forget the unit. So now we're done with nu1, and then we repeat for nu2. Okay, remember the first thing you have to do is what? You have to find out what's the phase of this point before you make a decision, before you plan how to look for this property. Okay, what's the phase of number 2? Let's go back to the diagram. Number 2 is right on the right side of the dome, so that's going to be G point. Number 2 is G point. Okay, how do you look for a property of G point? Table. Anything regarding F point and G point can be easily found from the table. It's table A2 or A3. When do you use table A2? When you want to start from temperature. When do you want to use table A3? When you start from pressure. So what do we know about point number 2? Do we know the temperature or do we know the pressure? 1 to 2 is a constant pressure process. and the pressure is 10 bar. So P2 must be equal to P1, which is 10 bar. So we know pressure. Okay, so now since we know pressure, we're gonna choose table A3. We know P2 is equal to 10 bar. And from here, you go to the table, and what do you look for in the table? Point 2 is just point G. So when you go to the table, you look for new G. You look for new G. All right, so let's go to table A3. Okay, so this is table A3, and we know we're going to start from 10 bar. 10 bar is already highlighted, 10 bar. And this time we're looking for a new G, and new G is in the fourth column, and it's 0.1944. Do not forget the unit, cubic meter per kilogram. So this is new 2. Go back to the notes and we write down new G, which is just our new 2. It's 0.1944. So now I have everything in the right hand side. P1, 10 bar. New 1 just found. New 2 just found. So I have everything in the right hand side. I can easily find work per unit mass. We plug in those three numbers. P1 is 10 bar, right? Make sure you do not use bar. You have to convert it to SI unit, which is Pascal. 1 bar is equal 10 to the 10 to the fifth Pascal. So times 10 to the fifth. That's Pascal. And then multiply by new 2 minus new 1. New 2 is 0.1944 minus new 1, which is 0.3066. Okay, and then you can use your calculator. The solution is negative 112.2 times 10 to the third. What should be the unit to the solution? Because I use SI unit for everything in the right hand side, then your solution must also be in SI unit. What is the SI unit for work per unit mass? For work, SI is joules. Divided by mass, the SI unit for mass is kilogram. Okay, and then the question asks for the solution in kilojoules per kilogram. So we convert joules to kilojoules. It's negative 112.2 kilojoule per kilogram. That's the solution. And now you notice your solution is negative. Doesn't make sense to have a negative solution. Okay? Negative means your system consumes work. Is it consuming work? If you take a look, 122 is what? 122 is a compression process. You compress the gas. The gas is being compressed, so gas is the one that is consuming work. And same thing happens in 223. So work has to be positive, consuming work. Okay, so that's question number 2, work per unit mass. And then number 3. Number 3 is to look for heat transfer, Q over M, Q over M per unit mass. Now I have work. From part 2, I found work. Part 3 asks for heat transfer. What equation should we use? We're looking for heat transfer, and I already have work. Which equation has both Q and W in it? Okay, and then the equation goes to our mind is probably first law. Q minus W is equal to delta E. Delta E has three components, delta KE, delta PE, and delta U. And double check it is a closed system. It is a closed system because the problem said so, right? Piston cylinder assembly, there's no inlet, no outlet. So it is a closed system. So yes, we can use this first law. And then, same as before, what can we do about delta KE and delta PE? First of all, the height doesn't change. The piston cylinder assembly, the height doesn't change. Height of the cylinder doesn't change. So there's no change of potential energy. Next one, the change of kinetic energy, delta KE. Initial velocity of the gas will be 0. Final velocity of the gas will be still 0. So 0 minus 0, there's no change of kinetic energy. All right, and then we're looking for heat transfer. So we move Q to the left-hand side, and everything to right-hand side is W plus delta capital U. Okay, and then we can continue. We can rewrite capital U into lowercase u. So it becomes mass times delta lowercase u. Okay, and what is lowercase u? What is delta lowercase u? Delta means change. So for change, it's always final, u2 minus initial, u1. And then finally, the question asks for Q per unit mass. So we divide every term by mass. Right-hand side first term becomes W per unit mass. Second term is plus U, oh, not U2, right? Be careful here because the final point is number 3, not number 2. Okay, the final point is number 3. We're talking about the whole process, 1, 2, 2, 2, 2, 3. So the initial point is 1 and the final is number 3. So it should be U3. Okay, and then divided by mass, it becomes U3 minus U1. Okay, so now we just need to find the 3 terms in the right-hand side, and then we can easily find heat transfer per unit mass. What about this one? W over mass? We just found it from part 2. We just found W over mass from part 2, so that's good. And then U1, U3, I don't have those two. This question goes down to looking for U1 and U3. Let's start from U1. U1 is the specific internal energy of point number 1, which is a property. Like we said, if you look for a property, the first thing you should do is to find out what's the phase of number 1. What's the phase of number 1? Phase of number 1, right? Go back to the diagram, you can see number 1 is to the right side of the vapor dome. So point 1 is superheated. If you're ever looking for any property of superheated water vapor, you should always go to table A4. When you use table A4, you have to provide 2 inputs, and one of them has to be pressure. And just like before, we know the 2 inputs. The first one is pressure. Initial pressure is given, 10 bar. The second input we have about number 1 is the initial temperature, given as 400 Celsius. And now you go to the table, you look for the corresponding U. Okay, so now let's go back to the table. Table A4 this time. Pressure is 10 bar. 10 bar. So this is the block, 10 bar. We're looking at 10 bar. It's highlighted already. And then the second input we have is temperature, highlighted 400 Celsius already. But this time we're looking for U. Where's U? U is in the third column. The unit is kilojoule per kilogram. So the corresponding U will be this one, 2957.3 kilojoule per kilogram. So now we can write down this corresponding U, and that is our U1. U1 is equal to 2957.3 kilojoule per kilogram. So now we're done with U1. We're done with U1. Then the only thing left in my right-hand side that I need to find is U3. As soon as I find U3, everything will be done. Okay, how do we look for U3? Again, just like before, if you look for a property, the first thing you have to do is to find out what's the phase of this point. What is the phase of number 3? Let's go to the diagrams. P versus nu diagram or T versus nu diagram, doesn't matter. On those 2 diagrams, you can see point number 3 is located within the dome. If the point is within the dome, then it must be a mixture. It must be a mixture. Okay. So now, if it is a mixture, how do you look for U? We gave you this equation earlier this week. If you have a mixture, you have to use the equation to find the corresponding U. All right, can you memorize this equation? Okay, U3.3 is a mixture. It has 2 components. What are the 2 components? The first one is the saturated liquid. You can call it U3F. The second component is saturated vapor, point G. So for this one, we call it U3G. Okay, and then how much G do we have? In other words, how much vapor do we have? That's the definition of quality. So we call it X3. And then how much liquid or how much F do we have? That's the rest. So it's 1 minus X3. Okay, do not forget the subscript for X quality. You need a subscript X3 because if you don't write a subscript, I don't know which point you're talking about, right? So make sure you write a subscript for quality X. Okay, let's take a look. If we can find everything in the right-hand side, then I can easily find U3. Okay, let's take a look. U3F, U3G. Like we said, anything about F point or G point can be easily found from the tables. So I don't worry about those two. I can always easily find those two from the table. However, X3, I don't know the quality of number 3. I know point 3 is a mixture, but I don't know the quality. I have to find a way to find a quality first, and then I can just plug in quality to the right hand side. Then I'll be able to find U3. How do we look for quality? How do we look for quality? This is a classic method. And this time we use a different property. This time, in order to find quality, we use a different property. We use nu3. We use nu3. Let's take a look. How do you look for nu3 for mixture? Same equation, two components, nu3f coming from the saturated liquid plus nu3g coming from the saturated vapor, and then percentage. I have x3, and then for f, I have 1 minus x3. Let's take a look at this equation. Is it possible for us to find x3 from this equation? First of all, nu3f, nu3g. About those two, like I said before, anything about point F and point G can be easily found from the table. So I can easily find those two. And x3, I don't have the one I'm looking for. Next one, what about nu3? What about nu3? Let's take a look. Let's go back to the diagrams. You can pick any one of them. For example, let's take a look at a T versus nu diagram. Remember, 2, 2, 3 is a vertical line. Vertical line. Why? Because 223 is a constant volume process. Constant volume process. And then the definition of nu is volume over mass. Volume doesn't change for 223. Mass doesn't change for 223. So specific volume nu doesn't change. So nu2 must be equal to nu3. Nu2 must be equal to nu3. Okay, so we know nu2 must be equal to nu3. And do we have nu2? Did we find nu2? Right here. We found nu2 from before. It's 0.1944 cubic meter per kilogram. So I do have nu2. And now if you take a look at this equation, how many unknown do I have? There's only one unknown, which is x3. So I can easily find x3 from this equation. So you perform the algebra. X3 is equal to nu3 minus nu3f divided by nu3g minus nu3f. And then we know nu3 is equal to nu2. So rewrite nu3 with nu2. Okay, I do have nu2. I found this one earlier. So what I need is just nu3f, nu3g, u3f, u3g. Okay, so how do we look for those? Point F or point G? What do we know about point 3? What do we know about point 3? The final point. Let's take a look. Point 3, what do we know? Point 3, water is cooled at constant volume to 150 Celsius. So we know the final temperature, which is T3, and that is equal to 150 Celsius. Okay, so we know T3, the final temperature. We know T3, which is 150 Celsius. So now you know temperature. If you start from temperature, which table do you go to? Do you remember? If you start from temperature, you go to table A2 for water. If you start from pressure, you go to table A3. Okay? And then from the table, what do we look for? We need to find nu F. So for us, we call it nu 3F. You also need to find nu G in the table. For us, we call it nu 3G. And then in addition, we can also find UF. And for us, we call it U3F. You can also find a UG, and we call U3G. Okay, so now we can go to table A2 and look for 150 Celsius. Okay, so this is table A2. This is table A2. And then we start from temperature, which is 150 Celsius. Where's 150? Right here. This is 150 Celsius. The four numbers we need are, this is new F, new F, new G. New G is here. And then UF, UF is this one. And then UG, UG is this one. Okay, so we copy down those four numbers. There's one thing you have to be very careful, that is new F, just in case you forgot. On top of the table, it says new F times 10 to the third. That means every number in this column has been magnified by 1000 times from the true value. So the true value for new F is 1.0905, and then don't forget, multiply by 10 to negative 3. You have to go back by 1000 times. That will be the true value. Okay, so now we copy down those four numbers in our notes. Nu 3F is equal to 1.0905 times 10 to negative 3. Don't forget that. Let me highlight this negative sign. Okay, and then do not forget the unit, cubic meter per kilogram. And then nu G from the table is 0.3928 cubic meter per kilogram. And then UFUG, UF is 631.88 kilojoule per kilogram. And U3G from the table is 2559.5 kilojoule per kilogram. So now I can plug in those new 3F, new 3G back into this equation, find x3. Okay, so what is x3? x3 is equal to nu 2. Nu 2, which we found from earlier, it's 0.1944 minus nu 3F divided by nu 3G minus nu 3F. So our solution for quality is 0.494, and quality doesn't have a unit. Quality doesn't have a unit. And then we can go back to this equation, plugging x3, u3f, u3g, and then we will be able to find u3. Okay, so u3 is equal to 1 minus x3 times u3f plus x3 times u3g. Okay, we're plugging everything. 1 minus 0.494 times u3f from the table, 631.88 plus 0.494 times U3G, 2559.5. Okay, be careful about those two numbers because they have the unit of kilojoule per kilogram. So our solution, which is 1584.0, must also have the unit kilojoule per kilogram because quality doesn't have a unit. Okay, so this is how you find U3. And now let's take a look back to this equation. Back to this equation. I have W per unit mass from part 2. I have U1 and I just found U3. I have everything in the right hand side, so I can just plug in those three numbers and find heat transfer per unit mass. Okay, so finally heat transfer per unit mass is equal to W per unit mass and then plus U3 minus U1. Okay, W per unit mass from before is negative 112.2. The unit was kilojoule per kilogram. Okay, plus U3. U3 is 1584.0. The unit is also kilojoule per kilogram. And then last one, minus U1. U1 is 2957.3. U1, yes. And the unit is also kilojoule per kilogram. So now our final solution for heat transfer is negative 1485.5. And then the unit to my solution must be kilojoule per kilogram. Okay, so that's the solution. And now you have a negative solution for heat transfer. What does that tell you? For heat transfer, if the solution is negative, that means your system loses heat. If your solution is positive for heat transfer, that means your system gains heat. Does it make sense for us to have a negative solution for heat transfer? Let's take a look. 122, what is 122? 122 is a cooling process, cooling, so lose heat. 2 to 3 is also a cooling process, lose heat. So 1 to 2 and 2 to 3 are both cooling processes. So 1 to 3 must be a cooling process. You must lose heat, and if you lose heat, the heat transfer must be a negative number. So it makes sense for us to have a negative number as the solution to heat transfer.